lecture, and this one is no longer about the matlab related stuff. It's I will try to show you how you can use programming libraries for solving some more advanced scientific and engineering problems. And those type of libraries are typically used when you need to embed some logic or some uh, more advanced, let's say, controllers. You need to build something into the real hardware. When you go outside the lab and you have real hardware which you need to somehow control, then you need to have proper tools for that will support you in the development process. So this is what I will try to do today, is to present some of those kind of tools that can be helpful, in my opinion. Um, okay, let's see how it looks. So first, I will mention about the physics engines. You probably may know from the game industry, but you can also use this for simulation purposes. Then I will present the linear algebra libraries, something which MATLAB is you were using for, right? For solving linear algebra problems, but not only. Next, I will present the Sandias library. Uh, this is the OD solvers, the set of solvers, OD solvers in C. Maybe I will also show how to solve ODEs in Python with C. There is IPOP. This is library for nonlinear optimization with nonlinear constraints, written in C++. And last is a CADO toolkit, which is kind of interesting library for model predictive control and moving horizon estimation, but not only. I will show what is capable to do for. Okay, so let's start with the physics engine. As I said, probably you heard about the physics engine because they are right now used in the game industry, especially Havoc and physics, which comes from the vendors. The physics is NVIDIA, and Havoc is the AMD. But on the market, there are also open source libraries which also have similar capabilities. Sometimes they have just different targets or has been designed to support different things. So the first one, Bullet, is the open source. I think right now is the most popular and alternative for physics and Havoc. You can find this physics engine library in many modern games. It's written in C++ and it has large community, so it's, in my opinion, is the first choice if you look for this kind of libraries and you don't take into account the vendor's specific closed source. The next one, ODs, this is the one of the first the library that was delivered available on the market. It still is supported. I haven't checked this recently. Uh, Bullet has much larger community, but the ODE was the first one which was really used and was open sourced. Next one, Box2D, is a specialized library for modeling the physics in 2D environments. All others which are listed here are designed for 3D support, but 2D sometimes is useful when you do the video games. Uh, Not all of those games use the 3D, but sometimes you also need to simulate the physics. So this is the library which address those kind of things, needs. Next one, Open Tissue. This is a library which support, which focus on modeling the soft objects. Um, this is typically hard, complex problem to solve to model the soft objects like fluids, like clothes, stuff like that. And this one was dedicated for modeling this kind of objects. Of course, those closed source physics have support this, probably Bullet as well, but the open tissue was the first one which was focusing on this problem. The next one is also very interesting physics engine. This is physics.js. This is library written in JavaScript. It means that you can embed physics engine into the web page. So you can build the web page, and you can uh, build the simulation environment in the web browser on the web page. This is something very interesting, and this library is used by several vendors to simulate the behavior of some objects on the web page, and then the web browser is the environment which allows you for running this. Very interesting, quite well optimized. It works quite good, uh, especially on the modern web browsers which use the hardware acceleration. So something I think worth trying if you are interested in the web technology. Havagon Physics, I mentioned those two. Uh, they are really very well optimized physics engine for hardware on which they will be used. They use the hardware acceleration by the GPUs. So those are, I think, the two best physics engine on the market right now, which are optimized for speed. The last one on this list, the Newton Dynamics. This is library which is more dedicated for scientific computation than for game industry, and it focuses on the accuracy, on the minimization of the errors. So if you really need to simulate truly the behavior of some objects, which best represent the behavior of the real object, the Newton dynamics is the library we should choose. So, and because there is always the trade-off, there is no perfect solution, at least right now. So you can have a speed or you can have accuracy. And most of those libraries focus on the speed, while Newton Dynamics focus on the accuracy and try to mimic the real world as much as possible. Of course, there are many other physics engines right now on the market. I just mentioned those specialize in some areas. Okay, the next thing that we should discuss is what kind of problems this kind of physics engine can solve for us. Generally, physics engine allows us for simulating the behavior of some object in some simulated environment. So you build the world, which you put some objects in this world and you simulate, and you want to see how these objects behave under some internal or external forces, or how they react one to another when you define some constraints, how they behave when they collide. So you can just simulate the behavior of some isolated elements in some world under some forces. To If you want to have this kind of library, what you need to do to achieve the same results, you need to write the equations of motions, constraints, collisions for all objects on the scene, and you can do it. But when you add another object, and you connect them somehow with joints or whatever, you define some constraints, those equations will dramatically change. So any small change in the world or in the scene you simulate require reformulate and rewriting of the whole equations. So this is, of course, very hard and in most cases even impossible to write all those equations. So this is why we use the physics engine to simulate the behavior numerically with some prescribed precision. Okay, so first, what this kind of engine or library needs to do is needs to solve the problem of the kinematic. What the kinematic is, have you heard about what the kinematics is? Typically, we define the kinematics in terms of the robotics. When you learn about robots, you learn about the kinematics. Have you heard about the kinematics? What is this? What it is? So when you have an object, right, it has some dimension, right? And when you connect another object, let's say this is the joint which can rotate. So we need to know how this object will move when this object is moving. Let's say we have another joint here, right? So we need to know where those objects are in the 3D space, right? Because this is somehow placed in the 3D space. So we can build this kind of chains, but we need to be able to calculate, knowing the angles in the joints, where each object is on the scene to be able to calculate its position and orientation, right? Because we need to know the position. This is one thing, like X, Y, Z, but we also need to know the rotation of this, how it is rotate. So we need to know the matrix of rotation, or maybe roll PGO, angles, or quaternion. So there are many different ways for how you represent the rotation. So we have R3 here, and we have spatial equivalent space as O3. So altogether we have spatial equivalent space here to represent the position orientations. So you need to be able to, even for presentation purposes, you need to know how to draw it, right? When those elements move. You probably had the same problems when you were animated the motion of the car, right? When the car is somewhere on the 2D plane, and when it's rotate, right? You need to know where all those uh, um, elements that you are using for drawing the represent the car are on the plane, right? You need to be able to compute the position of all those points somehow. So this is what the kinematic try to do. So it transformed the information like some dimensions, let's call it. We have lengths of our elements. We have also, let's say, angles, and knowing those information, we can compute where our end effector, let's call it, is in on the x, y, z plane plus rotation. So this is the transformation from dimension and angles to the, eventually we can have also position, we can have translational joints, not only rotational, so we can also translate, we can move it. So there's a mapping between position and angles to the of the joints to the position and angles of the end effector. Roughly speaking, this is not the precise definition. So this is what the kinematics try to do is try to describe the position of the objects when we know the angles and relation between those objects. This is first thing that you need to know when you simulate something. You need to know the relative positions, right, of objects. Then the second, and I think the most interesting for us, is the dynamics. So we can simulate the dynamics of the rigid bodies, clothes, fluids, and stuff like that. But what kind of problem or what we compute from the dynamics? What really dynamics do? What we can compute? Well, we have typically the equations which describe the motion of the objects. Let's focus on the rigid bodies. So we have a equation, right? This is inertia matrix. We have acceleration. We have Coriolis, right? We have gravity term. Let's call it G, whatever. And we have some external force. So we have our system of connected elements, and we apply some forces, or we can also apply the torques in the joints, right? And we can compute how the system is moving, right, under this forces. Sometimes we are also interested in opposite information. We would like to, we have some motion that we want to track, like somehow we design the trajectories for our system, right? We have trajectories for each joint in our robot, let's say, and we would like to know what kind of forces and what kind of torques will be generated or are required for this motion. This is needed when you design the, let's say, the robot. You have some masses, right, of the links. You know the maximal acceleration, maximal velocities, and you look for the motors which you need to put in the robot to be able to move along those trajectories, or to be able to move with those acceleration and those velocities. So this is what the dynamics is trying to answer, how object is moving under some given forces, or how it also we can simulate using dynamics equation. We can simulate other phenomena, but this is the different topic. Another thing is the constraints. Like I said, we to build the relation between two links in the robot, let's say, we define the joints. And when you define the joint, this is, in this case, this is a revolute joint, but we can have a translational joint, like we have something like that which can move this way. This is, we call this is the constraint. So we have two objects which are free floating, right? But when you connect them with the joint, then the motion of those two elements are somehow constrained by each other, right? Not all motions are right now possible. There are some energy transfer between those elements as well when you define this kind of constraints. So mostly those constraints relies to defining the joints or connection between the elements or rigid bodies, but not only. This is also used for simulating clothes and fluids, because we use very large mesh of elements which we define the constraints, how the energy is transformed between all those objects in the mesh. So the constraints are are needed to define this kind of stuff. And the last thing is the collision detection. This is something very something that we need for proper simulation of the behavior of the objects on the scene. in simulation, but also this capability is used in isolation by the planners. So when you build a planner for when you build a motion planner for the robot, you need to, for each position and configuration of the robot, you need to check if this position or this configuration is collision free, right? When you look for the collision free path, there are some objects, right? And you need to somehow navigate over those objects. If this is the robot, this is quite simple, but if this is the arm, which has all those constraints, right? We can't move in any direction, and this arm is also has some orientation. Then the planning in this space is very difficult, and you need to have some tools that will check the collision for you to plan the collision-free motion. And this is something also used in the simulation to proper model the behavior and the reaction of the objects on the scene when they just collide, right? You need to be able to detect this. You need to remember that we can simulate any object, right? The shape can be very complex, and there is no general formula which describe when the collision is or when this collision doesn't happen. There is no simple methods for that, and you need to use proper numeric methods or libraries which support this kind of problems. And physics engine deliver this kind of functionality, but not only, there are also standalone collision detection libraries which are used in robotic industry, but this is a different story. So let's stop here. Any question about that? Okay, let's move forward. So the physics engine, this is the library. This is something that you can use to build the simulation, but it doesn't allow you for simulating the whole world. I mean, you need to wrap this library with the API, right? With the GUI. You need to be able somehow to place elements on the scene, assign some attributes to the element like masses, inertias, define those constraints, apply the forces. So you need to have a simulation environment, or you need to build it by your own, just by programming this with use of the physics engine, or you can use the simulation environment which is already on the market, and there are several such programs that you can use on off the shelf. First one is Gazebo. This is the open source simulation environment right now. Gazebo, as far as I remember, it used the Bullet for physics, or it can use also the ODE. It's probably the selectable. You can choose which library you're going to use. It's integrated with the robotic framework, which we call ROS, if you are interested. So this is quite well integrated, so you can build the control system and model in ROS and then simulate in Gazebo. There is also the VREP, also recently open sourced. All this is it's free. You don't need to pay for using it. It's also quite well integrated with the ROS, so you can easily develop the system in ROS and then simulate it with VREP. Also, each vendor also has its own simulation environments. Microsoft has Robotic Developer Studio. LabVIEW has robotic module for simulation. There's the WebBots recently, which was also open source, but some time ago it was proprietary simulation environment. There's also the user scene, which used Quake engine for simulation, so it's quite well optimized for larger scenes. You can consider it for simulation your things. Um, MATLAB has also its physics engine and the module that allows for that. It's sim mechanics, as far as I remember. I haven't used it too much, but it's also something that is worth mentioning, that most of the vendors right now try to build such things because it's really simplify the process of developing the hardware. Generally, you need to know that typically when you test the hardware, first you need to do it in simulation, then you go on the real hardware and test something on the real hardware. Like I mentioned, maybe you do it first in the hardware in the loop and then on the real plant. But the simulation environment is something that you need to have and you need to know how to use in the engineering work, also in the scientific as well. Okay, so any question about that? Any question about the physics engines? Okay, if not, let's move forward. The next topic is the linear algebra libraries. Something similar to features that MATLAB has built into the language. But if you won't use the MATLAB, you need to and you will code in different language like C, C++, Python, Java, whatever. You need to have similar features, right? And the question is how to do it, how we can achieve the same functionalities which MATLAB has with use in of other languages. So linear algebra libraries is the answer for that. Most of the libraries that I listed here are developed for C++ or C. Okay, so the LAPACK is the library, one of the first. Originally is written in Fortran and has number of different wrappers for different languages. So you can use LAPACK in most modern languages, as far as I know. At least in C, in C++, there are wrappers for it, for LAPACK. This is very well optimized, mature library that probably is the first choice for someone who would like to use this kind of library in his project. But I personally prefer the Eigen, the next one. This is the C++ template library, which implement all the matrix vector operation, but also some more advanced things like solvers, um, um, the decomposition. So it it the this library is has very good. I mean, the performance is quite good comparing to other libraries. There is a lot of benchmarks that you can test. This library you can compare with others, um, especially on the very large problems, like you have matrix 1000 by 1000 or 100 by 100. So in this case, the performance is important, or you have sparse objects. So if you will code in C++, I strongly encourage to use the iGen. This is also the default library used in most robotic frameworks like ROS. This is the default used by others. And that this is the library I will show you on the next slide how to use it. The next one, microblast, is the part of the boost. If you program in C++, boost library, this is one. I mean, you should heard at least about this library. This is equivalent of the standard library. I'm not equivalent. First, something is introduced in the boost, and then maybe migrate to the standard library. It's very large template library which implement most of the things you need in the when you code in C++, and microplus is a part of this. So if you are using Boost, the microplus will be the natural selection. The next one, GSL, is the GNU Scientific Library, which is designed for C. So if you need the support for matrix and vector operation in C, the GSL is something you should consider in your project. Well, the API is quite complex and it's hard to use it, but it's off the shelf, so it has quite good benchmarks. Armadillo, this is very good optimized library within C++. And the next two, MKL and ACL, those two are vendor specific libraries, linear algebra libraries, which has been optimized for processor vendors. MKL is for Intel and AMD is for ACL. And in the benchmarks, they are just the best on a given platform. So if you really need if you know what kind of hardware you will use in your system, then you should consider those vendor libraries. They are just the best one. One maybe side note by Eigen. Eigen is very well optimized for different architectures. So you can just take the same code and migrate it to different architectures like x86 and ARM processor. It use all goodies that are delivered on or available on both platforms. So maybe it's not as good as the vendor, but it's very close. It's almost as good. So this is why I prefer the Eigen, especially when you write the code which needs to migrate or you want to reuse on different platforms. Okay, so here we have an example of Eigen in C++. As I said, this is the template library. So here we have an example how to define the 2x2 matrix. It's quite straightforward. You have the same API for setting the elements like in MATLAB. Of course, you start indexing with 0, this like we do it in C or C++ for other containers. There is also you can read the values of the elements of the matrix in the same way like in MATLAB. So I think switching from MATLAB to Eigen is quite straightforward. Here we have some more advanced operation like matrix vectors, transposition. So all those operations are supported in Eigen. Here we have also the inversion and determinant, so similar to MATLAB. And besides that, I can also implement the transformation and different representation of the position and orientation. So you can do the transformation between axis angle representation to the quaternion. You can define the rotation. So you can build the kinematics and compute the kinematics quite easily with use of the Eigen. This is why it's also popular in robotics. Okay, any question regarding the linear algebra? Okay, if not, let's move forward. The next library is the suite of the different solvers. Um, and the Sandials, this is the project which integrated many different solvers. All those solvers are written in C as far as I remember, so you can use it from C or C++. There are also wrappers for Python, and there is also interface for MATLAB, so you can use Sandials in MATLAB. And the question is why we need another ODE solvers in MATLAB while MATLAB has its own solvers, right? So the advantages of Sandials are twofold. So the first one is that it typically implement the state-of-the-art solvers. So there is a quite large community which try to keep this project in the loop, and it try to update and implement the uh, latest and the best solvers that was designed so far. This is one thing, and the second one that Sandial has unique features which other solvers doesn't have too often, or at least MATLAB solver doesn't have. They are able to compute the sensitivity of the ODE system, so we can check um, how the solution of some ordinary differential equation is sensible to change of the initial condition or some parameter. So let's say we have some ODE. That's right. We have some ODE. We have parameters, right? And what we do, we have some initial condition, right? And we simulate this over some time horizon. Let's call it capital T. And we look where we end up. This is, let's say, X final, right? This is what we do. And typically, or in some problems, we would like to know how this solution change when we change a little bit, let's say, initial condition. So how this will move, how much, right? Or eventually, we would like to also know how this whole solution change when we change a little bit the parameters. So how we call this kind of thing? Like we have some change, and we would like to know the change of the function. So how we call it? What it is when we have a function?
Uh, Derivatives describe the rate of change, but I don't
Yeah.
know if that.
This is typically in multidimensional when x is a vector. This is Jacobian. So if you want to compute Jacobian of the ODE, right? So we have differential equation, and you need to know Jacobian of this differential equation. You need to, in fact, compute the sensitivity. Why we do it numerically? Because typically we don't know how to solve the ODE in an analytical way. It's very hard to solve it, so we don't have the exact value of the solution, right? This is why we use ODE, and this is also why we need to use sensitivity analysis for computing the Jacobian of this system. When we need the Jacobian, well, if you will solve optimization problem, any optimization problem, like, and the ODE will be the constraint, like you have let's, I will present this on the next slide, but just would like to give you a hint what I'm talking about. Like we have some criteria, right? Let's say we want to optimize the control value. So we have some system, we have some controls, right? And it will be our unicycle. You have model unicycle, right? So this is differential equation, right? Our unicycle is function of time and x, right? And I have some parameters u. So we would like to find the optimal control for this system, and this is something that we need to do in robotics. We have the robot, right? And we would like to achieve some goals constantly continuously optimize the control values. So we would like to get here with the minimal control. So this is the problem we need to solve. So then the model of the system enter like in the form of the differential equation. And as you know, to find the optimal value, we need the gradient information and the Hessian. And in this case, you need to be able to compute the Jacobian. So this is the case when you need to be able to solve ODE with the sensitivity. And this is what Sandial solvers has. The standard CVO, the solver, this is the standard solvers like you have in MATLAB. So you have quite similar solvers like in MATLAB, maybe some advanced methods which implement more advanced methods, but most of them are also available in MATLAB. The CVO this is library which provide the same solvers with this sensitivity analysis capabilities. There are two way of computing the sensitivity. I don't want to get into details right now. You can read about that more, but this is something which is not present in MATLAB. MATLAB, for some reason, doesn't implement the sensitivity analysis. I don't know why, in fact. Okay, besides those two things, there is also the R-code, which implement the solvers for implicit methods. We have also solver for DAE system. This is our differential algebraic equation when we have differential equation ODE and we have some constraints, and this is something that we can also solve using Sandial solvers. Also with the sensitivity capabilities, so we can also compute the Jacobian. The last thing which is also included in this set of libraries is the KinSol. This is the library which solves the system of nonlinear equations. So we have, in fact, we solve the root finding problem for nonlinear system. So you have some complex system, right? And you want to find the zero of this system. This is also the problem that we quite frequently solve in engineering or so in the scientific world. One of this kind of problem is problem of motion planning. You define some error, like you have, let's say, mobile robot, right? You have some control and you want to get to some point, right? So the question is, what kind of controls you need to apply to the wheels to get to this point? So you define some distance to this, and you try to solve you write the equation, and you try to solve the problem that this distance is equal zero, right? When it will be equal zero, you will know that you are here at this point. This is briefly speaking how it works. So you can use this kind of solvers for solving the system of nonlinear equation. I don't know if I have mentioned how you can solve the root finding problem with the optimization techniques. Have I mentioned this somewhere or not?
I don't think so.
Okay, as a side note, maybe let's draw it here. Generally, we solve when you have nonlinear function, right? And you look for the roots of this function. This is root. Um, Depending where you start, you can you get to the zero, or even if you have something like that, maybe you won't find the zero because you will stuck in the local, we call this local minima. Uh, Typically, we solve this kind of problem with using gradient methods like Jacobian or Newton method. Probably you have heard about the Newton method to solve the root finding problem. But we can also, instead of solving a root finding problem, we can look for minimum of quadrat of that, sorry, so square of the function. So then this function is positive for sure, right? Because it's square, and we look for the minimum. And this minimum will be the one of the root of our system. Um, and this is the most, I mean, um, we can use the standard methods like Jacobian method or gradient-based method, which are quite good. But the best performance we achieve with using the optimization techniques for looking for root finding problems, for solving the root finding problems. The advantage of using the optimization technique is that you can define easily the constraints, because typically you optimize with constraints, and most of the solvers, uh, I mean, you can define the constraints in the natural way, while it's very hard to define constraints in the Newton method. In fact, Newton method don't allow you for defining the constraints directly. You need to do some magical things to include the constraints. So generally, you solve this root finding problem, solve unconstrained problems, and the benchmark shows that those optimization techniques has faster convergence. They converge from farther from the solution, starting from the solution. So they just behave better than the standard methods. Uh, the one limitation here is that you need to typically you need to assume that this function is double differentiable, right? Because you need to have Jacobian and Hessian, while here you only need to be one time differentiable, because you need to have only Jacobian. Okay, so that's it. Let's see how you can use the Sandials for solving the ODE. We have the unicycle model of unicycle. We will solve this on the horizon 1 second. We start from the initial condition 0, 0. We apply some constant controls. This is quite the same example like we had in case of MATLAB, and we look for the solution. And what I present here, this is some code. Maybe we won't get into details, and probably this is also the legacy interface. Right now they change a little bit the interface of the ODE, but this is not the thing that we should focus on right now. The thing is that we do some initialization here. We initialize the object that we will use for solving the ODE, and here is the place where we call the solver. And when we look at how it looks and what it require, it's very similar to the MATLAB solver. So you need okay, this is something maybe new. This is this object that we created here, but in fact it contains the information about our system. This is like the equivalent of this function in first element of the ODE in MATLAB is the function, right, which describes the right hand side of the equation. So as you see here, we create this object, and here we initialize it, and we initialize it with the function handler which compute our, this is right hand side. So this is equivalent. This is why it's the first element here. We also define here the initial condition. This is time 0, and this is x0, initial state. And when we call the solver, we ask the solver, okay, give me the solution at time te, and this is the state which will be written. So this is the output, in fact, and here is the time at which we get this state. A little bit different comparing to ODE in MATLAB is that you need to call it many times. Yep. Would you like to ask some question? Okay, maybe no. So in the Sandials, maybe what you need to know is that typically it can perform one step, and you need to evaluate it as many times to achieve the final time, or you can ask for solver to give me the solution at this time, and you get only the solution at this time. So it will integrate till the time, and you won't get any intermediate values, right? In MATLAB, you get those values as a return back, but in Sandials, if you ask only for this last point, you just get the last point. If you, and this is what it do, what this switch do, I mean the last element, last argument. So when you call it like this, instead of getting those values, you just will have the initial value, right, and the final value. This will be x at x0, and this will be x final. So if you want to get the intermediate points, you need to use the different parameters here, and you will need to call this solvers many times as long as this time achieve this time. This is something specific which you need to read about in the documentation. Maybe I don't want to get into too much details. Just mention this, that it's a little bit different in the behavior than MATLAB. And here is the implementation of the right hand side. So it just here we copy some initial the values from the argument to the local variables to better present the implementation. This is just the interface that this library use, so we need to follow it. Then we have the control. Here is the implementation of our unicycle, and then we store the result in the output variable, which is this is input, right? So this is like similar to MATLAB. We have time, we have x here, and we need to somehow return value here as well. In C, we can't return two elements like like we do in MATLAB. So in C, we return the output as an argument. This is the output. This is why we store the final those increments here in those variables, and we return 0 to say that everything is okay. And this can be used for passing the arguments. So if you have some arguments you need to pass, you can do it through this variable. So the functionality of the Sandials is quite similar. There are some differences. You need to read carefully the documentation, but the general idea is the same like in MATLAB. Maybe I will switch and show how you can do it, how you can solve the OD in Python. Let me share the terminal. I don't have slide for that. Sorry, I just read what Kamil Śmigielski has read in the in the chat. Um, Kamil, you are here, right? Would you like to elaborate a little bit more about what you just said in the?
Well, I worked a little bit with Gazebo, and it's uh, it's hard to define strict constraints for the nodes of what we are working with. Uh, you are almost forced to depend on the physics engine with everything.
Yes, but in the component that I cooperate, we are using Gazebo for simulating quite complex robot. With the full use case tests, I mean, we have the environment model, we have robot, we have all sensors, we have actuators, and all. I mean, the algorithms are first tested in simulation in Gazebo, so it's doable. I don't say it's simple, but there are not too much alternatives, to be honest. You can use VREP. This maybe it's not super fast and super optimal. I mean, you need to have quite powerful GPU like NVIDIA, which is supported, but it's usable. You can run also you can define tests, right? Like you test programs, like you write the unit test, right? You can use Gazebo for testing some uh, integration stuff, right? When you have a robot or you want to test some different piece of code, how they behave in the scenarios, you can use Gazebo on the CI, I mean the continuous integration, to test if everything is fine. Without the simulation, you are not able to run any integration test. I mean, you can do unit tests, but integration is very hard. So with the simulation, it's at least first step for integration tests.
Yes, I just wanted to point out that with Gazebo, because it depends on physics. Like when we did the car, the practice tasks for the
Mhm,
class, we could just say that our like some point is somewhere exactly,
mhm,
and we need to follow this point,
mhm,
this some path. In Gazebo, you are forced to be to base everything on physics, on
mhm.
the physics engine.
Yep, that's true. I mean, simulation of the cars, generally the non-holonomic system is not simple. I mean, it's very hard to model these contact forces between the ground and the wheels. Uh, there is a quite interesting paper about the simulation in general, um, which use position-based dynamics. I don't know if you have heard about that. The guys has created very powerful algorithm for simulation the physics, the full physics, and this is it works especially good in for non-holonomic systems. They have simulation on the internet in the YouTube where show the very complex systems which simulate on CPU without the GPU. It's amazing, in fact. But okay, this is different story. Let's stop here. Let's move with the ODE um, in Python. So here I have IPython. So in Python, you have some tools for solving the ODEs. I will use SciPy. SciPy is I mentioned this somewhere probably where I was talking about the matlab. So this is the library which implements it's scientific library which implement a lot of goodies. So we will write the right hand side function right now. This is very simple function. Um, so the API is just the same like in MATLAB. So first we have time, state, and some parameters, and this is the exponential, right? So the equation is like, oops, sorry. We have something like, let me annotate. X dot is equal minus px, right? So this is exponential function like this, and depending on the p, we have a different slopes here, right? So this is this function. Okay. So we define some time horizon. We have some initial state and the parameter. Okay, and the solver is just the same like the API of the solver is the same like we have in MATLAB. So here is called solve initial value problem. This is the name of the function which can be used. Also, there are different APIs for that, but this is, I think, the most straightforward. First, we pass the function the right-hand side, so just the same like in MATLAB. Then we have the time horizon, the initial condition, and we pass the arguments. This is maybe something Python specific. And here we have the solution, so probably print T contains the time samples and Y contains the solution. So we can print it probably, yeah, like this, plot, yeah, okay, one, I don't remember. Let me check how we can plot it. What do we have here? I know. Once again, plot Y. What? Okay. Plot Y. What is this? Okay. Got it. So it's 0. It's alright. Oh, it's fine. Okay. Right now we can plot it. Oh, you won't see it, right? Sorry for that. So this is how it looks. So yeah. So in Python, solving the ODE is very, very similar to solving in MATLAB. So API is quite the same. The function names is a little bit different. So there are also some difference with respect to the language, right, usage, but general approach is the same. Okay, so any question about that?
I guess not.
Okay, so let's move to the optimization solver. So I present here the iPopt. I think this is one of the most popular open source solver that is able to solve the nonlinear optimization with nonlinear constraints, where the constraints can be the equal or inequality, the form of equality or inequality. This is, I think, the most general form. So probably you can fit most of the problems to this one. Maybe iPod won't be the optimal for, I mean, the sense that won't you solve it in the best way, but it will be able to solve it, right? With the optimization, there are some methods which are dedicated for given class of the problems. And iPod, I think, is the most general. The alternative to the iPod, there is let me annotate. So iPod use interior point method. This is one of the methods of solving this kind of problems. And alternative to this is SQP. This is sequential quadratic programming, which is also very powerful. And SQP is used by the Acado. For some problems, one is better and other is better for other problems. So it depends on the problem. Generally, they are comparable. So depending what you will do, probably you may have some little bit results with the SQP, but iPod will probably also be able to solve your problem as well. So iPod, this is the C++ library, the project within C++ is object-oriented. So you will define the problem in form of the C++ class. Okay. So here we have example. We will solve this problem. This is our criteria that we minimalize. We have 4-dimensional problem, but iPod deals without any issue with very large problems as well. So you can solve large problems with hundreds or thousands of variables. And here we have a constraints. We have one equality and one inequality constraint. And we have also some bounds on the variables. And as in most numerical methods, you need to provide some initial condition from which you start the optimization. So you need to provide the gradients of the function you minimalize, also the gradients of the constraints. And here is you need to unfortunately compute it by hand. I mean, you need to provide the information about those gradients. There are some ways of avoiding this. Probably iPod can compute it by itself using the final differences, or you can use the automatic differentiation. I haven't mentioned about the automatic differentiation libraries, automatic differentiation, and you can use AD libraries for computing the Jacobians for you. But this is information you need to provide to iPod. Okay, let's move forward. So we have the Jacobians, and here is the class that you need to define. You need to define your problem in form of the class. You inherit the base class, which is the general description of the optimization problem. As you see, there are some methods that you need to override, and those methods will deliver the information about your problem to the iPod. So all of them needs to be implemented by the user to properly inform about the problem. And we will go over those methods to see what is there. First is the general information about the problems, the dimension of the problem, number of constraints. We need to inform also how many elements about the sparsity of the Jacobian, how many elements of the Jacobian are not zero, and also provides information about the Hessian. Then we have information about the bounds. So here we define our constraints. Then we have the initial condition. This is another method. Here we implement the function which we minimalize, the gradient of this function, and the value of the constraints. Those are equation of our constraints. And here is the Jacobian of the constraints. Maybe one note about this Jacobian. Typically, when you have very large optimization problems, the Jacobian of constraint is sparse. It means that it looks like that you have almost all zeros in the array or in the matrix, and somewhere you have some values, right? Some of those elements are non-zero. Why we have this kind of it's true because when you define constraints, you don't take all variables in all equation. Like you have constraints, let's say x1 plus x2 plus x3 and so on, right? So you don't do the same, you don't define the same constraints using all those variables in all other use cases. So typically you have some combination, 1, 2, 3, right? When you have very large problems, hundred of or thousand of the independent variables, then this Jacobian is really sparse. So only some elements are non-zero. So here they use a notation which provide the position and value of the object, and you use a triple notation. So when iPod would like to know which element is not zero, so we call this this part, and this part provides information about the coordinate of this object. So it provides when we have iRow and iCall, it says that element 0, 0 is not 0. Then we have another element 0, 1. Then we have 0, 2, right? 0, 2. Then we have 0, 3, which is not 0. And we have 1, 0, which is not 0, 2, 1. In fact, the matrix is dense, so all elements are non-zero. So this is the list of elements, list of coordinates of elements which are non-zero. In our case, unfortunately, all elements are non-zero, so we have dense Jacobian. So this is this part. But also we need to provide the information about the value of the Jacobian, and this is when this function is called with values, not null values. I mean, this is not the pointer is non-null. Then you need to return on proper elements value of the element. So when the first element was 0, 0, so then you need to provide on this position the value of this element. Let's say value of 0, 0. So 0, 1, you need to provide the value of 0, 1, and so on and so forth. So we use a triple notation to describe the value of the one element. So you can ask why they use this kind of notation. Well, when the matrix is dense, this value, I mean this notation has large overhead, right? Because instead of storing one value, we need to store value plus 2 indexes. So we have, let's say, row, call, and value, right? But when the matrix is sparse, and this is what typically is true in the large problems, and this is where the solver is typically used for large problems, this list is very short. I mean, we have only several elements which are non-zero, so the list is very short, and instead of having 100 by 100 values, we can have, let's say, 10 times 3, right? So instead of storing 100 by 100, we store only, let's say, 30 or 40 elements. It's much better for large problems, sparse problems. Okay. let's move forward. We have 15 minutes, and this is the function method which is called at the end when the solver finds the solution. Any questions about that? I know this is a little, brief for you. You are not familiar with the API. This is just the example which should work out of the box. Just copy pasting it to the editor, compiling properly, and it should just work. You can learn more when you will going to use it. I just present what you need to be prepared for when you're going to use this kind of tools. Okay, the last library is the Acado Toolkit. This is also the collection of different libraries, which has some nice functionalities. First, it's designed for nonlinear optimal control. Also, it is able to solve the multi-objective optimal control. What is the multi-objective optimal control? This is the problem when you have some sequence of optimization problems. Of course, you can solve them. Each problem you can solve independently, but the global solution won't be optimal. So when you will solve each problem independently, it won't be the global optimal for the whole system. And this is the system you want to optimize. So you need to use different methods which will look for the global optimization of this sequence of optimization problems. And this is what Acado provides tools for. So you can solve the chain of optimization problems when each problem depends on the solution of another problem, right? So this is very complex problem in general. You can also use the Acado for state and parameter estimation. This is something which is very needed in the control and in the robotics. You can use also model predictive controls. And this is, I think, right now the state of the art, the best methods for full control of the nonlinear system with some when you have lack of knowledge about you don't have full knowledge about the system parameters, or you don't know all elements of the system. So the model predictive controller is the best controller you can build, and it, in fact, achieve the best performance. Of course, compared to it's general. So of course you can build some dedicated controller for given class of the system, but if you don't know how to build this controller, the model predictive, I think, is the best one you can build. And the last but not least is the feature is that you can first design, you can simulate your system, you can build the optimization, you can use a proper optimization techniques, you can build estimator, and at the end you can generate code which will be for a nonlinear model predictive controller and for moving horizon estimator, which you can use in the embedded system in the real time. So this is the code, very well optimized. You can wrap into the when you have let's say some components framework, you can wrap into the component, connect to your system, and use without any other modification. So you can very fast prototype and deploy the very complex control algorithm to your embedded system. This is something what we need in the robotics, for example. Okay, so what kind of problems we can solve? We will minimize some criteria. We'll look for the optimal control. And our criteria is following. So we have some end term. So the end term, this is something what will happen at the end of the time horizon. This is the term which forced to achieve some goal position. So we have some desired position, QD, and we start somewhere, right? And we want to reach this position at the time t. So this is the state which we would like to have at time t. And along this trajectory, along this path, we will constantly minimize the control. So we look for the minimal control. This is the problem we're going to solve. And the constraints are following. First, the constraints define the model of our system. In our case, it will be the probably unicycle, as far as I remember. So this is the equation which describes the motion of the unicycle. We have some bounds, final bounds, how precise we need to reach the goal, right? Because we can say that we need to reach it precisely, but we can say that, okay, when we reach it in the region, it will be also fine, right? So this is something we constrain. And we also define some upper and lower bound on the control, because as you know, each physical system has some bounds. You can't apply any control, so you need to take those constraints into account when you prepare the planning. So we will solve this kind of problem with this tool. And here is the implementation. It's C++, so it has defined objects which define the differential state, control. Also, you can has something which we call intermediate variables, but here we use only differential state and control. Here is the place where you define the equation, the right-hand side. This is the right-hand side of our system. The notation is quite interesting, right? It's very descriptive, at least for me. You can read what how this differential equation looks like. That is just the standard thing. We define some initial condition. This is the those are the function which describe those terms, the first one and the second one. Then we have both are the quadratic in the quadratic form, so those are the functions. We have the final state. We define the constraint, our matrix, and here is the code which in fact define the whole problem. We build the optimization object on some time horizon. We define our terms. The end term, it was the h1. It was defined here. Sorry, here. It was the state, and this is the this term. Sorry, this term is defined here. Then we defined our minimization. Sorry, our constraints. So this is this piece which defines the constraints. Then we build the algorithm object and then call solve for this problem. So this is more or less how it looks in the code. And with this code, I mean, most of the code is just the initialization. Here is in fact, the place when you define our system. So this is the most important part, and this one which defines the whole problem. So let's say we have around 20 lines of code, which will solve quite complex control problem. We optimize here. So you may ask why we don't need to define the Jacobian and Hessian, right? In the IPOP case, we was forced to use it. And here we just define the F, right? We don't need to calculate the Jacobian of the F. You don't need to calculate Jacobian of the constraints. In this case, this is the differential equation, so it's quite difficult to compute this, right? So the Acado use the automatic differentiation, as I mentioned. So it has inbuilt automatic differentiation. So this is why you need to use this state objects for defining the ODE, and then based on those variables, Acado is able to compute the gradient and Hessians without need of defining them explicitly. So this is a very nice feature that Arcado has. I haven't mentioned this is the control problem, but also you can use Arcado for estimation. Why you need estimation? So in control, when you control something, what you have some actual state, right? You have some desired state, or we typically write that we would like to. This is this is desired, this is actual, this is where we are, this is where we would like to be, and this is error, right? This is something, the error we would like to go to zero. And the thing is that what we did here, we built the controller which will drag the error to zero. But to do so, you need to know where you are. So you need to be able to measure your actual position, orientation, I don't know, the state of the system, whatever it is. And the question is how to measure this. Typically, in the most cases, you can't directly measure the state. It's impossible. I mean, there is no such sensors which allows you for measuring the full state of the system in most cases. So you can't assume that you can just measure it. Even you have some, even if you have some measurement capabilities, probably you need to filter this, right? It's noisy, or sometimes the information is missing. You don't have this information all the time, or the frequency at which you get this information is different of the frequency of the controller, because you need to know that this control is working on the, should work on the high frequency, right? Like 10 kilohertz, 100, sorry, 100 hertz or 1 kilohertz, right? So this is typical frequencies at which we run this kind of stuff. So the question is how you can get this state. And in most cases, you need to estimate the state. So you measure something else, like you measure acceleration, and based on the acceleration, you can estimate the position and velocities. Or you measure some velocities and you estimate position. Or you have a different sensors, you have some laser scanners, and you can measure some distances to to some objects, known objects, and based on that you can do some triangulation or trilateration, and you can measure your position with respect to those objects. So there are many methods. You can also use the model of the system, like you have the motion equation, like dynamics of the system, and you know that this system can move different because the dynamics constrain the motion, right? You can't accelerate in very fast because you have, let's say, large mass, right? This is something that you can also use for estimation. And the Arcado implements something what we call moving horizon estimation. And this is something opposite to the predictive control. In the predictive control, you look in the future to find the optimal solution. And the moving horizon estimation, you are here, you measure at something, right? Here, and you want to know how you achieve this. You look in the past, so you try to feed your model best to the data you collected so far. And you can use moving horizon estimation for estimating the state, but also unknown parameters of the system, because you can look for the parameters which best describe the measurement you have. Why we would like to do it together with the estimation of the state? Well, because our model can have some parameters which are unknown, like you have the mobile car, right? And you don't know the contact forces between the wheels and the ground, because depending on the ground type you move, you have different contact forces. And you need to know those contact forces to measure to model or to simulate the motion. And unfortunately, you don't know those contact forces, so you need to somehow estimate them. So the moving horizon estimator is one of the method which allows you for this, and it do it with the optimal way. So it use model information, it use measurements. You can measure different things. You don't need to directly measure what you need to for, or you need to measure. I mean, what you need for your state, right? And you can also get the state. So this is something very interesting. I think it's worth to know that such algorithms exist. Okay, so this is it from my side. Any questions?
I have one question, but it's about laboratories.
Yep.
So are we supposed to, in this Simulink task, are we supposed to make animations?
Yes, please remember that you can always store data in the workspace, MATLAB workspace. And if you have data in the MATLAB workspace, you can do whatever you like from that.
Okay, so just use the
right?
same movie function.
Yes,
just
exactly.
Okay,
yeah,
okay. Thank you.
Course, yeah. Anything else? If not, that's it for today. Thank you very much. Bye.
Thank you. Goodbye.
Thank you. Goodbye.